Welcome to this problem walkthrough. Today, we'll be solving LeetCode problem number 16, titled Threesome Closest. In this problem, we aim to identify three integers in an array such that their sum is closest to a given target. We'll explore the approach step by step, analyze its complexity, and discuss when to use it. Let's dive in. The goal of this problem is to find three integers from the input array nums such that their sum is as close as possible to the given target value. Once we've identified this closest sum, we need to return it as the output. The problem guarantees that there will always be exactly one unique solution, so we don't have to worry about ambiguous cases. The input consists of an integer array nums, where each element lies between -1000 and 1000, and the array has a length between 3 and 500. Additionally, the target value is an integer within the range of -10,000 to 10,000. The output will simply be the integer sum of the three numbers that are closest to the target. To understand the problem better, let's look at some examples. In the first example, the input array is nums equals -1, 2, 1, -4, and the target is 1. The sum of the three integers closest to 1 is -1 plus 2 plus 1 equals 2. This is the best possible sum because the absolute difference between this sum and the target, that is, 2, 1 equals 1, is smaller than for any other combination of three numbers from the array. Therefore, the output in this case is 2. Another example helps clarify further. Here, we have nums equals 0, 0, 0, and the target is 1. The only possible sum we can create from this array is 0 plus 0 plus 0 equals 0. Since there are no other combinations to consider, this sum is trivially the closest to the target. The absolute difference between the sum and the target is 0, 1 equals 1. So the output here is 0. In the next example, we see a case where the target lies far outside the range of sums achievable with the given numbers. For instance, if nums equals 1, 1, 1, 0, and the target is -100, the closest sum is 1 plus 1 plus 0 equals 2. Even though this is far from the target, it is the smallest possible sum based on the array values. The absolute difference in this case is 2 minus 100 equals 102. Thus, the output is 2. To solve this problem, it's important to consider the constraints and edge cases. The constraints specify that the array length will always be at least 3 and at most 500, and all values in the array, as well as the target, fall within a specific range. The guarantee of one unique solution ensures we don't have to handle ambiguous outputs. For edge cases, we need to consider scenarios such as all negative numbers in the array, where the target is also negative, or all positive numbers, where the target exceeds the sum of the largest elements. Another case might involve duplicate numbers in the array, which must still be considered as valid candidates for forming sums. Lastly, arrays filled with zeros require attention to ensure the closest sum is correctly identified when the target is a non-zero number. These considerations help ensure the solution is robust and handles all possible inputs effectively. To tackle the threesome closest problem, the goal is to identify three integers in the array whose sum is closest to the given target value. One way to approach this problem is by using a brute force method. The intuition here is straightforward: examine every possible combination of three numbers from the array, calculate their sum, and determine how close that sum is to the target. The process involves three nested loops that generate all unique triplets, followed by computing the absolute difference between the sum of each triplet and the target. Throughout this process, we maintain a record of the closest sum encountered. While this method is simple and ensures we explore every option, it's computationally expensive, as the time complexity is O(n cubed, due to the large number of triplets in larger arrays. Additionally, it has a space complexity of O(1), as no additional data structures are required. However, its inefficiency for larger arrays makes it unsuitable for practical use in most scenarios. A more efficient approach to solving the problem is to use the two-pointer technique combined with sorting. The key insight here is that sorting the array allows us to systematically narrow down the search space, significantly reducing unnecessary computations. To implement this approach, we start by sorting the input array. Then, for each number in the array, we consider it as the first number of a potential triplet. Using two pointers, one initialized just after the current number and the other at the end of the array, we search for the other two numbers that bring the sum closer to the target. The two-pointer technique adjusts the pointers dynamically based on whether the current sum is less than or greater than the target. This ensures that we efficiently explore possible combinations without needing to evaluate all of them explicitly. This method has a time complexity of O(n squared, where sorting takes O(n log n, and the two-pointer search for each element takes O(n), making it far more scalable than brute force. In terms of space complexity, the two-pointer approach is highly efficient, as it operates with a space complexity of O(1). This is because it only uses a few variables to keep track of indices and sums during the computation. One of the major advantages of this method is that it is significantly faster for larger arrays compared to brute force, as it systematically reduces the number of combinations to evaluate. Additionally, the sorting step ensures that the search space is well structured for the two-pointer technique to work effectively. However, it is worth noting that sorting modifies the input array, which could be a concern in certain scenarios. If preserving the original array is necessary, we can work with a sorted copy instead. Overall, the approach is not only more efficient but also practical for real-world applications where input sizes can be substantial. The two-pointer approach with sorting emerges as the optimal solution for this problem because it balances efficiency with simplicity. By leveraging the insight that sorting the array enables dynamic pointer adjustments, we avoid the exhaustive evaluations required in brute force. This drastically reduces the computational complexity to O(n squared, making it well suited for larger inputs. While the brute force method is easier to understand and implement, it is impractical for large arrays due to its O(n cubed complexity. On the other hand, the two-pointer approach is slightly more complex to implement but delivers significant performance improvements. This trade-off makes it the preferred solution for the three-sum closest problem, as it ensures accurate results within a reasonable runtime. In conclusion, the two-pointer technique combined with sorting is not only efficient but also scalable, making it the best choice for tackling this problem. To solve the three-sum closest problem, we need to identify three integers in the array whose sum comes as close as possible to the given target. The most efficient way to achieve this is by combining sorting with the two-pointer approach. First, we sort the array. Sorting is essential because it allows us to efficiently adjust two pointers to either increase or decrease the sum based on how it compares to the target. For instance, if the current sum is too small, we can increment the left pointer to explore larger values. Sorting typically takes O(n log n time using a built-in algorithm like timsort in Python. After sorting, we initialize a variable called closest_sum to infinity, which will act as a reference for tracking the best possible sum we've found so far. This setup ensures that we have a structured way to compare potential sums during the main iteration of the algorithm. Once the array is sorted, the next step is to iterate through the array to evaluate different combinations of three numbers. For each number at index I, we treat it as the first number in a potential triplet. From here, we use two pointers to identify the other two numbers that might form the closest sum. The left pointer starts immediately after I, and the right pointer begins at the end of the array. This setup creates a dynamic window that we can adjust based on the current sum's relationship to the target. For example, if the sum is too small, we move the left pointer forward to increase the sum. If it's too large, we move the right pointer backward to decrease it. The two-pointer technique ensures that we systematically explore all possible combinations without the need for nested loops, making the approach both efficient and elegant. Now, within the loop where the two pointers are active, the algorithm calculates the current sum by combining the values at I, left, and right. We then compare the absolute difference between this sum and the target with the absolute difference of the closest sum found so far. If the current sum is closer to the target, we update closest_sum to this value. Depending on how the current sum compares to the target, we adjust the pointers. If the current sum is less than the target, we increment the left pointer to consider larger numbers and move closer to the target. Conversely, if the current sum exceeds the target, we decrement the right pointer to consider smaller numbers. If we find an exact match, that is, the current sum equals the target, there's no need to search further, and we can return the closest sum immediately. After iterating through all possible triplets, the algorithm concludes by returning the closest_sum. This value represents the sum of the three integers that are closest to the target. The approach works efficiently due to a few key principles. First, sorting the array allows the two-pointer technique to function correctly by preserving the relative ordering of elements. Second, the greedy refinement of the closest sum ensures that every adjustment to the pointers moves us toward an optimal result. Additionally, the algorithm can terminate early if an exact match is found, saving unnecessary computations. Finally, edge cases are naturally handled by the problem constraints, such as ensuring that the input array always contains at least 3 elements. Duplicate values in the array also don't impact the logic, as every triplet is explicitly evaluated. This robust framework ensures both correctness and efficiency. The algorithm operates with minimal data structures, making it memory efficient. The input array is sorted in place, and the two-pointer approach works directly on the array indices. The only additional variables are closest_sum, which tracks the best solution so far, and the left and right pointers used for adjusting the search space. Regarding complexity, the algorithm's time efficiency is a combination of the sorting step, which takes O, n log n, and the main loop. The loop runs O, n, iterations, and for each iteration, the two-pointer search operates in O, n, resulting in an overall time complexity of O, n squared. The space complexity is O, 1, since no extra memory is allocated beyond the variables. This combination of quadratic time and constant space makes the algorithm highly scalable for moderately sized inputs. Let's walk through an example to see how the algorithm works in practice. Suppose the input array is -1, 2, 1, -4, and the target is 1. First, we sort the array, resulting in -4, -1, 1, 2. We initialize closest_sum to infinity. In the first iteration, with I equals 0, we set nums, I, to -4, left to 1, and right to 3. Testing the sum -4 plus -1 plus 2 gives -3, which updates closest_sum to -3. Incrementing left gives a new sum of -4 plus 1 plus 2 is equal to -1, updating closest_sum again. When left equals right, the loop ends. In the second iteration, with I equals 1, nums, I, is -1. Testing -1 plus 1 plus 2 gives 2, updating closest_sum. Decreasing right ends this loop. After all iterations, the result is 2, demonstrating how the algorithm narrows down the closest sum systematically through sorting and pointer adjustments. Here, we begin by defining a class called solution and implementing the 3SumClosest method. The first step is sorting the input array, which is crucial for applying the two-pointer technique efficiently. After that, we initialize a variable called closest_sum to infinity. This will help us keep track of the sum that is closest to the target as we iterate through the array. The main part of the solution involves a loop where we treat each element in the array as the first number in a potential triplet. For each of these elements, we set up two pointers, one starting just after the current element, called left, and the other starting at the end of the array, called right. Using these pointers, we can explore all possible pairs that, together with the current element, form a triplet. Inside the loop, we calculate the sum of the current triplet by adding nums, I, nums, left, and nums, right. If this sum is closer to the target than our previously stored closest_sum, we update closest_sum to this new value. To refine our search, we adjust the pointers based on how the current sum compares to the target. If the current sum is smaller than the target, we move the left pointer to the right to increase the sum. If the current sum is greater than the target, we move the right pointer to the left to decrease the sum. This way, we progressively narrow down the possible triplets. Now, if we ever find a triplet whose sum is exactly equal to the target, we immediately return that sum because it's the closest possible value. This is handled in the condition where current_sum equals the target. If no exact match is found after iterating through the array, the method returns the closest_sum that was recorded during the process. This ensures that the result is the triplet sum closest to the target after evaluating all possible combinations. The algorithm is efficient, leveraging the sorted array and two-pointer approach to avoid unnecessary computations, making it suitable for a variety of input sizes. Here, we start by importing the necessary Java utilities and defining our solution class. The method 3SumClosest takes two inputs, an array of integers nums and an integer target. The first key step is to sort the input array, which allows us to efficiently use the two-pointer technique later. Sorting ensures that the numbers are in ascending order, which simplifies the process of finding combinations. Next, we initialize a variable called closestSum to integer.max_value. This will keep track of the closest sum we've encountered so far to our target value. We also define n as the length of the array for clarity and efficiency. Now we iterate through the array using a for loop, where each element in the array is treated as the first number in a potential triplet. For each of these elements, we set up two pointers, left starting at the next index and right starting at the end of the array. These pointers help us explore different combinations of three numbers. Inside the while loop, we calculate the current sum using the values at the I, left, and right indices. If this current sum is closer to the target than our previously recorded closest sum, we update the closest sum variable accordingly. We then adjust the pointers based on whether the current sum is less than or greater than the target, which helps narrow down our search range for the closest sum. If the current sum is less than the target, we move the left pointer one step to the right to explore larger sums. On the other hand, if the current sum is greater than the target, we move the right pointer one step to the left to reduce the sum. These adjustments continue until the left and right pointers meet, ensuring that all possible combinations with the current I value are considered. Now, there's a special case where the current sum exactly matches the target. In this scenario, we know that this is the closest possible sum, so we can immediately return it without further calculations. Once the loop completes, and we've explored all potential triplets, we return the closest sum, which holds the value closest to the target. This approach effectively balances accuracy and efficiency, leveraging the sorted array and the two-pointer strategy to reduce the time complexity compared to a brute force solution. To solve the problem, we start with an example where the input array is -1, 2, 1, -4, and the target is 1. The first step is to sort the input array, which gives us -4, -1, 1, 2. Sorting is crucial because it allows us to efficiently use the two-pointer technique. Next, we initialize a variable called closest_sum to infinity. This variable will help us track the sum that is closest to the target as we iterate through the array. Now, we begin iterating over the array using an index I. For each I, we set up two pointers, left, starting at the index immediately after I, and right, starting at the end of the array. This setup helps us systematically explore all possible triplets in the sorted order. In the first iteration, we set I to 0, so nums, I, is -4. The left pointer starts at index 1, nums, left, equals -1, and the right pointer starts at index 3, nums, right, equals 2. We calculate the current sum as nums, I, plus nums, left, plus nums, right, which equals -4 plus, -1, plus 2, giving us -3. Since the absolute difference between -3 and the target, 1, is smaller than the difference between infinity and 1, we update closest_sum to -3. Because the current sum is less than the target, we move the left pointer one step forward to index 2. Now, the new current sum becomes -4 plus 1 plus 2, which equals -1. Again, we update closest_sum to -1 because the difference between -1 and 1 is smaller than the difference between -3 and 1. Moving the left pointer forward once more brings it to index 3, which ends this iteration. In the second iteration, I is set to 1, so nums, I, is -1. We position the left pointer at index 2, nums, left, equals 1, and the right pointer at index 3, nums, right, equals 2. The current sum is calculated as -1 plus 1 plus 2, which equals 2. Since the absolute difference between 2 and 1 is smaller than the difference between -1 and 1, we update closest_sum to 2. This time, because the current sum is greater than the target, we move the right pointer one step back to index 2, ending this iteration. At this point, the loop concludes, and the closest sum is found to be 2. In this example, we are given the input array 0, 0, 0, and a target value of 1. The array is already sorted, so no additional sorting is needed. We initialize closest_sum to infinity, as before. Next, we begin iterating through the array. For the first iteration, I is set to 0, so nums, I, is 0. The left pointer is positioned at index 1, nums, left, equals 0, and the right pointer is positioned at index 2, nums, right, equals 0. The current sum is calculated as nums, I, plus nums, left, plus nums, right, which equals 0 plus 0 plus 0, giving us 0. Since the absolute difference between 0 and the target, 1, is smaller than the difference between infinity and 1, we update closest underscore sum to 0. Because the current sum is less than the target, we move the left pointer forward to index 2, which concludes this iteration. As there are no further indices for I, the loop ends, and the closest sum is determined to be 0. In this example, the input array is 1, 1, minus 1, minus 1, 3, and the target is minus 1. First, we sort the array, resulting in -1, -1, 1, 1, 3. As usual, we initialize closest underscore sum to infinity. Then, we start iterating through the array. For the first iteration, I is set to 0, so nums, I, is -1. The left pointer begins at index 1, nums, left, equals -1, and the right pointer starts at index 4, nums, right, equals 3. The current sum is calculated as nums, I, plus nums, left, plus nums, right, which equals -1 plus -1 plus 3, giving us 1. Since the absolute difference between 1 and the target, -1, is smaller than the difference between infinity and -1, we update closest underscore sum to 1. Because the current sum is greater than the target, we move the right pointer one step back to index 3. Now, the current sum becomes -1 plus -1 plus 1, which equals -1. This is exactly equal to the target, so we update closest underscore sum to -1 and immediately return -1 as the closest sum. Since we found an exact match, there is no need to continue iterating. To summarize the results, for example 1 with nums equals -1, 2, 1, -4, and target equals 1, the closest sum is 2. In example 2, where nums equals 0, 0, 0, and the target is 1, the closest sum is 0. Finally, for example 3 with nums equals 1, 1, -1, -1, 3, and target equals -1, the closest sum is -1. These examples demonstrate how the solution efficiently finds the closest sum using sorting in the two-pointer technique. The time complexity of this solution is primarily determined by two main components: sorting the array and the nested iterations that follow. First, sorting the array takes n log n time, as it uses an efficient sorting algorithm. After sorting, we have an outer loop that iterates through the array up to n 2 times, which contributes n. Within each iteration of this outer loop, we use a two-pointer approach to traverse the remaining portion of the array. This traversal takes linear time, or n, for each iteration of the outer loop. When we combine the time complexities of the outer loop and the two-pointer traversal, we get n times n, which equals n squared. Although sorting contributes n log n, it becomes negligible compared to n squared when the input size is large, so the overall time complexity is n squared. The space complexity of this solution is 1, as it uses a constant amount of extra memory. The input array is sorted in place, so no additional space is required for storage. The algorithm only uses a few variables, such as closest underscore sum, current underscore sum, left, and right, to store intermediate results during execution. Since these variables do not depend on the size of the input array, their space usage remains constant. Additionally, no extra data structures are used, further ensuring that the space complexity stays at 1. For the best, average, and worst-case scenarios, the time complexity remains consistent at n squared. Even in the best case, where the target might be found early, the algorithm still processes the entire array. Similarly, in both average and worst cases, the two-pointer traversal completes its iterations, maintaining the same n squared complexity. When compared to a brute force approach, the optimized two-pointer solution demonstrates significant improvements in efficiency. A brute force method would iterate through all possible triplets in the array, checking each sum against the target. Since there are n choose 3 combinations, this approach has a time complexity of n cubed. In contrast, the optimized approach leverages sorting and the two-pointer technique to avoid exploring all combinations. By narrowing the search space, it reduces the time complexity to n squared, making it far more scalable for larger input sizes. To understand the mathematical proof of the big O here, sorting takes n log n, the outer loop runs n times, and for each iteration, the two-pointer traversal contributes another n. Combining these results in n log n plus n asterisk n, which simplifies to n squared. Once again, O n squared dominates O n log n, confirming that the overall complexity is O n squared. When working on the threesome closest problem, there are a few common mistakes to watch out for. First, not sorting the array can lead to significant issues. The two-pointer technique relies on a sorted array to ensure that adjustments to the pointers are systematic and effective. Without sorting, the pointer movements become unpredictable, leading to incorrect results. The fix here is simple: always sort the input array before applying the two-pointer approach. Next, a common misunderstanding arises with the calculation of closest. Instead of directly comparing sums, the correct method is to compare the absolute difference between the current sum and the target. This ensures you're properly evaluating how close the sum is to the target. Lastly, skipping duplicate elements is essential for efficiency, but it's easy to make mistakes here. For instance, skipping all occurrences of a number might cause you to miss valid solutions. The correct approach is to only skip duplicates while adjusting the pointers in the sorted array, which avoids redundant calculations without overlooking potential answers. Another mistake to avoid is not handling edge cases properly. For example, if the input array has fewer than 3 elements or contains extreme values, your solution might throw runtime errors or produce incorrect results. To address this, always add checks for the array length and test your code against edge cases, such as very large positive or negative target values. Additionally, relying on a brute force approach can be problematic for large inputs. While trying every combination of 3 numbers might seem straightforward, it's O n cubed. Complexity makes it impractical when n is large, such as 10 cubed or more. Instead, use the optimized two-pointer approach, which reduces the time complexity to O n squared after sorting the array. From an interview perspective, it's important to recognize that sorting simplifies the problem and enables the efficient two-pointer strategy. Be prepared to discuss how you handle edge cases, such as arrays with fewer than 3 numbers, and ensure you understand why using absolute differences is critical for correctly calculating the closest sum. To deepen your understanding of the threesome closest problem, it's helpful to explore related problems that build on similar ideas. For instance, problem number 1, two-sum, involves finding 2 numbers that add up to a specific target. This is a foundational problem that introduces the concept of pairing numbers efficiently. Next, problem number 15, three-sum, focuses on finding all unique triplets that sum to 0, which is directly related to threesome closest but emphasizes identifying all valid combinations. Problem number 18, for sum, extends this idea further by asking for unique quadruplets that sum to a target, increasing the complexity slightly. Finally, problem number 259, three-sum smaller, challenges you to count the number of triplets whose sum is smaller than the given target, which is a variation that tests your ability to adapt the two-pointer approach. Practicing these problems will reinforce key techniques and prepare you for variations you might encounter. There are several approaches to solving the threesome closest problem, each with its own trade-offs. One approach is brute force, which involves using 3 nested loops to try every possible combination of 3 numbers and calculate their sum. While this method is simple to implement, its O n cubed time complexity makes it impractical for large input sizes. A more efficient approach is the optimized two-pointer method. Here, you sort the array, fix 1 element, and use 2 pointers to find the closest sum for the remaining 2 elements. This approach reduces the time complexity to O n squared, but requires the array to be sorted beforehand. Lastly, there's a less common approach that uses hashing. By storing sums of pairs in a hash map, you can check for the closest sum to the target. However, this method increases space complexity and is less intuitive than the two-pointer approach, making it less favorable, particularly in an interview setting. Understanding these trade-offs will help you choose the best method based on the problem constraints. Great job following through. To summarize, we've used sorting and the two-pointer approach to solve the threesome closest problem efficiently. Keep practicing similar problems to strengthen your understanding. If you enjoyed this walkthrough, be sure to like, subscribe, and share. Thanks for watching, and happy coding! That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!